Welcome to threads mapping section. In this section, we are going to learn how the threads are going to map on the compute resources. As you can see in this figure, this is the software entity and entire this part is your hardware entity. So, this is representing threads block, means the group of threads in a block. When this block has to be mapped on SM, again I am repeating, this threads block must be mapped on SM. So, for simplicity, I am just considering in my SM has only one process block. Generally, there are there may be a 2 process blocks, there may be a 4 process block, but for simplicity, I am just considering that each SM has one process block to make you understandable how the flow works. So, before actually mapping on this compute cores, these are the actual compute cores. Before mapping the threads on the actual compute cores, threads has to flow to the warp scheduler, and this warp scheduler divides the number of threads in a block into the chunks of 32. For example, suppose I have only 128 threads per block, and then when it will go to the warp scheduler, so warp scheduler will divide into 32, 32, 32 and 32 chunks, means it will be divided into the 4 warps. So, basically warp is a group of 32 threads. That is the smallest unit which is processed inside the SM. Similarly, instead of 128 threads, you can make it 256 threads per block. In that scenario, the total number of warps will be 8 warps, and so on. So, that means warp is one entity, you can say it is again a kind of hardware or software entity that is executed physically in parallel on the streaming multiprocessor. But interestingly, number of warps per block is limited by the maximum block size, and it is different for different GPU architecture. Not only the architecture may be different for specific GPU models. So, in this case it is always recommended to refer the data sheet to understand what is the maximum block size is supported by the underlying GPU architecture, and accordingly how many warps can be produced or can be generated in this flow. So, now let us try to understand how this flow of warps works with a small example. I am just considering I have taken 2 instruction dispatcher, but in some GPU there may be only 1 instruction dispatcher. Suppose I have a program, in this program has 3 instructions. Instruction 1, that is a load operation, instruction 2, that is a add operation, instruction 3 is a again store operation, and I am applying it on the warp 0. I have just taken only warp 0, it has 32 threads, and each thread has to perform these 3 instructions. So, in this scenario what will happen, I am just ignoring the second instruction dispatcher for a moment, I am just focusing on the one instruction dispatcher I have. In this scenario, so when any warp will come, then particular instruction, suppose instruction instead of 2 here is a 1, instruction 1 will be processed. When one instruction 1 will be completed, then instruction 2 will be processed, so on until the entire warps completes its entire operations. Because there is no independent operations are there, each one is dependent with each other. So, warp 0, for example, I am taking thread 0, thread 0 has to perform load operation, thread 0 will perform the add operations, and then it will perform the store operation. But along with that, if one more instruction I add and which is independent, again I add the another add operations, but it is independent of this one. I am just taking instruction 4. This instruction is independent of the instructions 2. This data is totally independent, and I am considering both the instruction dispatcher. So, in that scenario, if this is my instruction 2, suppose this is a warp 0, I am making it 0, and this is also warp 0, because these two instructions are independent, then the instruction, this instruction 2 is processed, then instruction 4 will be processed by the another instruction dispatcher. So, this kind of activities are performed by the architecture itself. Programmer has no need to think about all that, but understanding is important. So, that is why we can say the order of execution of the warp is arbitrary. Usually it depends on the operand's readiness and the required processing units availability. Let us suppose here this instruction dispatcher working on instruction 0, thread 0, and both operations are add operation. So, this is going to put a resource limitation. Data is ready, but processing elements are not available because instruction 2 is utilizing those resources. So, again a bottleneck. So, what you can do, if your program has a multiply operation, so in that scenario both are independent and both required different unit of computation. So, in that case both dispatcher can dispatch and both the operations, operation 2 and instruction 2 and instruction 4 will get their resources and they will perform concurrently or simultaneously. Role of instruction dispatcher. Instruction dispatcher mainly performs 4 different operations. It decodes and issues the instruction, manages the multiple threads, handles dependency and hazards, and interleave warp execution. So, basically instruction dispatcher decodes the instructions fetched from the instruction cache and issue them to appropriate execution unit, and it ensures that instructions are sent to the correct execution unit such as integer, floating point, tensor core, load or store units. Manage multiple warps. As you know that each SM can handle multiple warps simultaneously, So, instruction dispatcher selects one or more warps to execute in each clock cycle based on the readiness and resource availability. We just discussed about that. Dispatcher consider factors like data dependency, instruction latency, memory access delays, and available execution units to make its selection. Next is handles dependency and hazards. It identifies the data dependencies and pipeline hazard, which just I discussed in this part here. Here you can say, instead of this, earlier I was performing the add operation. So, there is some kind of dependency on resources. So, such kind of dependencies are handled by the instruction dispatcher. And dependencies of pipeline, that part I will cover in the next section, when I will cover in detail the dependencies on the pipelining units by taking different examples. Interleave warp execution. To keep all execution unit busy and hide the latency, the dispatcher interleaves the instruction from multiple warps. For example, if one warp is waiting for data to be fetched from the memory, the dispatcher can issue instructions from another warp, ensuring that the execution units are always occupied. So, let us discuss, or we can say that how to calculate the number of warps. Here you have launched the 3 blocks to an SM, and each block has a 256 threads. So, number of blocks and number of threads in each block, it is flexible, user can define it. Suppose as a user I have declared 3 blocks and to be assigned on each SM, each block has 256 threads and I have only one SM. Then how many warps are there in an SM? So, very simple, we have to divide the number of threads available in the block by the warp count, that is 32. So, there will be a 32 warps in each block, but since we are assigning 3 blocks to an SM, so there will be a 24 warps will be assigned or mapped onto the SM. Now, let us consider the scenario. We have 4 process blocks in an each SM. So far, I have just considered, to simplify the explanation, I have just considered only one process block, but now I am just considering the 4 process block in each SM. You can see here SM has a 4 process block, and each process block has their own warp scheduler, if you are able to see these orange color boxes. And I launched the third block, it has 128 threads. You can see the thread T0 to 128 threads in each block. If I launch the third block of size 128, then this 128 threads will be divided into 4 warps, you can see, and this all 4 warps will be mapped on each warp. This is called warp 1. I just, so you can say here, this will be mapped on warp 0 on this process block. There will be a warp 1, warp 2 and warp 3. If I double this number of threads up to 120, 256, if I want to launch 256 threads per block, then there will be a total 8 warps, and then I am just for explaining purpose I am just mapping the values like warp 0 and it will be warp 4, warp 5, warp 6 or warp 7 will be mapped, but order may be anything. One process block may be 0, may be 1, that will be taken care by the warp scheduler. Now, let us discuss the warp level flow diagram and pipelining. Again, for simplicity, I have made some assumptions here, and this part if you see, this is a portion of each process block. If you see here, L0 cache, this 4 thing you can see here, L0 instruction cache, warp scheduler, dispatch unit, register files, and then they are the execution units. So, I have mentioned this is a L0 instruction cache, there is a warp scheduler, dispatch unit, registers. After the registers there are execution units. In each core there are 2 types of operations are possible. First is addition and second one is the multiplication. And another assumption I made that because generally there is a more clock cycles are taken, but to make the explanation simpler, so I have just considered that the load operation will considering 4 clock cycles, add and multiplication operations are taking only 1 clock cycle, store operations is also taking 1 clock cycle. So, let us see this operation, how this operation will be flow in the form of warps. If I am just considering the 1 SM and 1 process scheduler, it is also it is 1 not 4, I am just assumption I just consider it as a 1 clock cycle. Let us see, I have to perform the operation of addition of 2 array A and array B and store the result into the array C, and I am considering there are 160 elements in my array. If I divide 160 element by 32, you are get the 5 warps. So, why I have just numbered the warp 0, warp 1, warp 2, warp 3 and warp 4. Let us discuss. Suppose this first clock cycle is I will just write like clock cycle 0, warp 0 comes to the dispatch unit and dispatch unit identifies that check that data is available or not. If data is not available inside the register, then it is going to perform the load operation. And in cycle 2 it is happening. Next, at the same time, as same cycle, warp 0 comes to the dispatch unit and it will also check that whether the data is ready with the for the warp or not. So, again data is not ready. So, in clock cycle 3, warp 0 and warp 1 is waiting for the load operations to be complete. At the same time, at same cycle, warp 2 comes to the dispatch unit. In the next clock cycle, CY3, warp 0, warp 1, warp 2 all are waiting for the load operations to be finished. Load operation means data is available in your memory and it is to be bring it to the register. But at same time warp 3 is ready, warp 3 go to the dispatch unit and check for its data is available or not. In the next clock cycle CY3, warp 0 has successfully loaded its data from its memory to the register. And warp 3, warp 1, warp 2, all these 3 warps, warp 1, 2 and 3 is waiting for the data to be loaded into the register, and same time warp 4 is come to the dispatch unit and it is checked for its data present or not. The next clock cycle CY4, warp 0 will go for the addition unit, warp 1 will load the data into the registers successfully, and warp 2, warp 3 and warp 4 are waiting for its data to be loaded into the register. In next clock cycle, you can see that warp 0, the computation on warp 0 has been successfully completed. So, it came to the store unit, warp 1 came to the execution unit where addition to be performed, and warp 2 load operation is performed, data is loaded from the data memory to registers. So, at this time you can see that load operation, store operation and warp execution operation or computation operation are working at the same time. So, this is the way the warps are flow through the various pipelining stages. For simplicity, I have just considered, again I am stressing that for simplicity I have just considered only one process block of the SM, and number of process blocks can vary from GPU to GPU architecture to GPU various GPU architecture or even model to model, and even the instruction dispatcher number may vary 1 or 2. Based on that and what kind of operations you are going to perform, that also influence the entire performance of the GPU. So, similarly, if all cycles the operation will be performed, you can check in every clock cycle, after that all 3 units are busy simultaneously. So, what are the important observations are here? Overlapping execution. As soon as the threads finish one stage, just like load stage, they proceed to the next stage, multiply, add, addition stage, and new threads enter the first stage. This interleaving basically hides the latency and improve the throughput, because all 3 units are using simultaneously. Next observation is the pipelining and latency hiding. The warp scheduler issues instruction for different pipelining stages in successive cycle, allowing the memory bound and compute bound operations to overlap. Generally, memory bound operations always needs more number of clock cycles compared to the compute bound operations. Efficient resource utilization. By overlapping the load operation with computation, warp scheduler ensures that the memory units and FP64 QNITs are efficiently utilized and reducing the idle time. So, these are the important observations from the warp level flow diagram and pipelining stages. So, there is one important note. The NVIDIA GPU can perform operations on different type of cores concurrently. That is a feature that has been added from V100 onwards. While FP64 cores are busy with double precision operations, FP32 and INT32 cores can handle single precision and integer operations respectively. Let us see this small program. Everybody is familiar, this is a for loop program. and for loop is used to execute the loops. But if you look at this for loop very carefully, there are two types of data types are available. First is the loop driver, that is int I, that is an integer type, and this will be processed by int 32 that I mentioned. At same time, within that there is an operation, multiplication operation is happening. When one data element of array is being multiplied by 2.0, this is a 64 unit I am assuming here, 64 FP64 core is utilizing for this operation. So, that means at the same time these 2 units can be used for this kind of operations. So, in 32 core we will continuously increment the value of I, and this operation continuously bring the data from the respective locations and it will be multiplied by the 2.0. So, that is the reason this note is mentioned here that so different type of cores concurrently operate, whether the operation is being done by FP64 at same time FP32 and int32 cores can also be utilized for their respective operations like single precision and integer operations. Let us discuss the intra warp scheduling. This is another scenario. So far we have discussed about the warp level scheduling, when warps are being scheduled on the resources with the help of warp scheduler. Here also warp scheduler come into the action, but we have to look more minute level. To make it again simpler, what I have considered here, each operation, load operation is taking 1 clock cycle, multiplication also takes 1 clock cycle, addition also takes 1 clock cycle, and store operation also 1 clock cycle. These are the pipelining stages. So, what I have thinking at one stage, one warp which has 0 to 31 threads has been loaded. 32 threads data is loaded, that is available in the register file, and I am assuming that all the threads has to use the FP64 compute cores. But problem is that there are 32 threads, but actually if you look at, there are only 8 FP64 cores that can be used. Then how it will be utilized? So, that is the reason this 32 threads will be again divided into the another chunks of 8 threads based on this computing resources. In first cycle, first 7 threads, 0 to 7 threads will go. In next cycle, 8 to 15 threads will go. In next cycle, 16 to 23 threads will go. At last, 24 to 31 threads will go in a fourth cycle. When all the threads will complete its operation, it will be clubbed together and store operation will be performed. It is a scenario when I am using FP64 cores. Suppose instead of FP64 cores, I want to utilize only FP32 cores, this portion of the code, and there are total number 16 such cores are available. In this scenario, my 32 threads will be divided into the chunks of 16 and 16, and 16 in one cycle and another 16 in another one cycle. So, total 2 cycles. So, that means it giving the one illustrations like that. If I am using FP64, if I write a program and I force my program to use only FP64 core for same number of array addition or matrix multiplication. So, FP64 will take longer time in computation as compared to FP32 because of this limitation. So, this comparison we will discuss while discussing the programs. So, in next section I would like to discuss the warp overlapping with the help of various examples or various examples, you can say various algorithms. Very small algorithms I will consider to explain how the warps are getting overlapped in those scenarios. Thank you.